We will continue our study of the sweep paradigm. In the last lecture, we have seen a line sweep algorithm for the line segment intersection problem. Today, I will give you another application of sweep paradigm, that is, we will construct what is called visibility polygon. Okay. So I will define what it is. This is not a line sweep algorithm. Instead, this is a ray sweep algorithm. In a ray sweep algorithm, what happens? Let us think of a point P and a ray emanating from P. Okay. This ray starts maybe in the horizontal position towards right and makes a complete rotation by 360 degree. So, this may be the direction of rotation. Of course, it can be in the other direction also. So, during the movement of the ray, sweep of the ray along this entire 360 degree, certain events happen and we catch those events. Okay, so this is the difference between a line moving from minus infinity to plus infinity and a ray making a 360 degree rotation. Okay, so let me introduce the problem first. Okay, let me bring this picture. This one, yes, this one. That will be smaller. Okay. Okay. So, what I am given is a polygon, this blue. You can assume that this is the boundary of a room. Okay, typically we do not see such rooms, but it may be an art gallery, something like that, a museum, where you have different chambers like this. Okay, so the input consists of two things: a simple polygon this blue thing specified by a, or in brackets, clockwise listing of the corners or vertices. Okay, but clockwise we have seen does not make enough sense. By clockwise that meant if I follow this listing, then this the interior of the simple polygon will always remain to my right. So it is this direction. This. Okay. So this sequence of vertices is provided such that if we move along the boundary following this listing, the interior will be always to my right. So this is one part of the input, and the second input, a point P in the interior. Suppose that you are sitting here, a guard is sitting in a gallery or museum somewhere here. Okay. So the idea is which part of the interior the guard can see. That is once again a polygon, not necessarily simple. Simple but not necessarily convex. Here in this picture, so output is the visibility polygon. The region in the interior. Visible to P. So this is once again a polygon or polygonal region, as you can see in this example. And we will specify this once again by outputting its vertices in the same clockwise order. I mean, whenever. So it would be maybe something like this, so that this visibility region will always remain to my right. Okay. Definitely, this problem makes little sense if the input is convex. Then, given any point in its interior, you can view the entire interior of the convex polygonal region. So the output is same as the input. Therefore, we will typically assume that this is the input polygon is simple but not convex, something like this. Okay. So, I will have a sweep algorithm where P is the point from which this ray emanates and makes a complete 360-degree rotation. Okay. So, I will give you another picture which summarizes it all. Yep. Something like this. Okay. So, this is the starting position, horizontal starting position of the ray starting from P, emanating from P. And this is the sweep direction, which we assume clockwise. And now, the events that occur during this rotation of the sweep ray are precisely these vertices Q1, Q2, Q3, Q4, Q5, Q6, Q7 and so on. So, the sweep ray, the events are the corners or vertices of the input polygon. Moreover, like that sweep line information, we will maintain a sweep ray information. Sweep ray information, which is nothing but the set of active edges of the input polygon. So, what is active? If an edge like Q1, Q2, Q2, Q3, if they intersect with the current position of the sweep line, okay, then that edge is called active. Otherwise, it is non-active or passive. So, in the starting position, this Q5, Q6, Q4, Q5 and Q2, Q3 are the only 3 active edges. Okay. So I am not talking about this direction. The ray is always starting from a point and looking at this direction. If I extend it backward, there will be other edge intersections, but I will not consider those. So Q5, Q6, Q4, Q5 and Q2, Q3. These are the 3 active edges at the beginning. Okay. Okay, so active means that. And when does this set of active edges change? It changes whenever an event occurs. So that is, we reach a boundary, and then you may be leaving some edge and entering a new edge or something like that. Okay. So what I will do, so events are characterized by some point Q I. Okay, let us call it Q. It is some Qi. For example, the first event that will happen, okay, and the events are sorted with respect to their angle measured in this direction, starting from the horizontal right position. So the first event turns out to be the event Q4. Okay. Second event will be Q3, Q6. Q7, Q8, Q9. So this way the events are ordered with respect to their angle extended between this horizontal position and this PQ line. Okay. So if Q is something like QI, so I look at Q, let's say minus, which essentially means the point Q I minus 1 and Q plus, which essentially means Qi plus 1, but this I minus 1 and I plus 1 should be computed on this. So for Q1, Q minus 1 is Qi minus 1, this is Q14, not Q0, Q2. Likewise, for Q14, the next vertex is not Q15, but Q1, previous one is anyway Q13. Okay. So, Q minus and Q plus are this I minus 1 and I plus 1 are on the circle. Okay. And we call the edge Q minus Q to be E minus and Q plus to be E plus. Okay. For example, whenever this event Q1 occurs, the edge Q14 Q1 is my E minus and Q1 Q2 will be my QE plus. Okay. Okay. So now let us see how we can handle an event. Okay. Now I will come to individually 4 types of events, but let us see that what is the relative position of Q minus and Q plus with respect to the sweep line. If the event is Q1, you see that Q14 is to the left of this ray, whereas Q2 is to the right of that ray. Okay. So, with respect to the position of the previous point and the next point on the boundary of the room, this is, if it is Q1, we call this an event of type LR. Q1 is to the left, Q minus is to the left, Q plus is to the right. And many of these things are like that. Q2 is also like that. Q3 on the other hand, you see that both Q2 and Q4 are to the left of this ray at this position, Q2 and Q4. So Q3, sorry, this is Q1, I should write, Q3 is of type left, left. And if I look at Q5, at this position, what happens? Both Q4 and Q6 are to the right. This is the ray, so this is to the right, this is to the right. So Q5 is an event of type R. Whereas if I look at this Q4, here what happens? The previous one is to the right, the next one is to the left. So this event Q4 will be an event of type right, left. Okay. So before going to handling each of these events individually, I mentioned that if it is L, whenever I have L, here or here or here, okay, it essentially implies that I am leaving some edge. Okay. So for example, Q14 was active before Q1 happens, but since it is to the left and this sweep line will anyway move to the right, so Q14 will no longer stay active. Okay, so left means leave segment, this kind of, or a leave edge. And right, if I am right, after this Q1, Q2 will remain active. Okay, for some time at least. So this is leaving, this is entering. So here, previous point, previous edge you are leaving, the next edge you are entering. This is previous edge you are entering, and next edge you are leaving. Yeah. Here you are leaving, you are entering both the previous edge and the next edge, and here you are leaving both the previous edge and the next edge. Okay. So with this understanding, let us see how to handle these events. So first, the most simple thing, LR. Okay. So here we see two instances of the event LR. Previous one is to the left, next one is to the right. Here also previous one is to the left, next one is to the right. Q1 is another such thing, Q2 is another such thing, but anyway, these two examples are good enough. So this is an event of type LR. So what we will do, this is left, right. So S, remove E minus, insert E plus. But then, after we are done with this, you find out whether this point of intersection, from this point onward, E plus will stay for some time. It stay in this sweep ray information. It will stay active for some time. Then you see whether this E plus is the closest. Okay, so I am sorry, I forgot to mention one thing. S is always kept sorted. Yeah, I forgot to mention this. S is kept sorted with respect to, in the ascending order, of course, with respect to their distance, their distances from P along the ray or current position of the ray. Okay. This sorting we should maintain. Okay. So now I identify after inserting E plus whether E plus is the closest edge in the sweep ray, along the sweep ray, closest among all the active lines. If so, I will add Q9 to the output, as is the case here. This is the, at this point actually this is the only, E plus is the only active region, and therefore it has to be the closest. So I will add Q9 to the output polygon. On the other hand, if I am in a situation like Q12, this is also LR, but at this point, immediately after this event, there are three edges that are active. This one, Q9, Q10, Q10, Q11, Q12, Q13. It turns out that this Q12 is not, Q12, Q13 is not the closest edge with respect to this distance from P along the current position of the ray. Therefore, I will not add this point to the output polygon. Okay. Okay, so add Q to output if and only if E plus is closest to P. Okay, and of course I am also maintaining this set of events, so I will come to that, how to organize this event queue. Okay, so having seen an LR type of event, let us see the next type. Again, I import a picture, RL. Okay, so this Q4 illustrates this. The previous point is to the right, the next point is to the left. Okay, so it seems that this is rather symmetric to the LR case, but it is so. So in the sweep line, this is RL. So you insert L is leaving, so insert E minus and delete E plus. Okay. Now then the question is whether you should insert this point, Q4. Okay. So that is a little bit of imagination. You see that if this happens to be the closest point to P among all the active lines, then P is outside the interior. It is impossible. Okay. If such an event occurs, it is impossible that this is the closest I would say segment on the, with respect to this sweep ray. If so, this P is outside the interior. Okay. So you just insert E minus and delete E plus. That's all. Nothing else you need to do. Okay. So in this case, E minus cannot be closest to P. So there is no question of adding any point to the output polygon. Okay. So this event is even simpler than LR. Okay. Okay. Remove what? This is remove insert and this is insert remove. Okay. So now let us see a slightly more complicated case, LL. Okay. Okay. So in this case, the effect on S is definitely you have to you are leaving both E minus and E plus. Okay. So you have to remove or delete both E minus and E plus from S. Okay. But before removal, both E minus and E plus were active. Okay. So do this thing before removal. Yeah. Do this. Check whether E minus or E plus was closest to P. Okay. If not, I have a situation as in Q3. The closest segment is Q5, Q6. Neither Q3, Q4 nor Q2, Q3. So do nothing. Otherwise, okay, you add this point Q10 and then after removal, check whether it was closest to P. So if not, you are done. Otherwise, after removal, you find the closest edge and the intersection of the ray, the current position from Q10 to from P via Q10, and wherever this intersects, this point and this intersection point you output. Okay. So after removal, find the intersection of the ray with the closest active edge. Okay. Intersection, let us call it R. So output this Q and R in that order. Okay. So left event can also be handled, slightly more complicated than the earlier ones. So this leaves us with our final event type, that is RR. Okay, let us see what happens when we do handle such an event. Okay, yeah, so in this position, both Q4 and Q6 are to the right. Here also, both Q10 and Q12 are to the right of the ray. Okay, so what should we do? First of all, this is RR, therefore I must insert both E minus and E plus to S. They will now become active. Okay, you are entering. To consider here, after this point, you make a sweep further, they will continue to remain active for some time here also. Okay. Then, as you see, before the, okay, so the next question is, so S is always kept sorted with respect to their distance, with respect to the distance of the active lines from P along the ray. At this point, both E minus and E plus are equidistant from P. So in which order I will insert? Okay. So for that I have to be a little bit futuristic. I will compute this angle PQ here, of course, PQ5, Q6 and PQ5, Q4. Whichever is smaller, okay, this angle, in this case PQ5, Q6 is smaller, so this will be inserted before E plus. Sorry, this is E plus. Okay, for Q5, E plus and then E minus. Whereas if I look at this Q11 case, if I compute this angle PQ11, Q10 and PQ11, Q12, this angle is larger. Therefore, I will insert E minus earlier, then E plus. Okay. So, this is how I settle this insertion order. For Q12, first E minus, then E plus. That will be the future order. Okay. And then, before doing all this business, we will again find out whether E minus or E plus is the, okay, after insertion we do it. Okay. Before that they were not active. So, after insertion, check whether E minus or E plus, whichever is earlier, is closest to P. Okay. If not, as in this case, Q11, do nothing. Okay. Do not output anything to the any vertex to the output. Otherwise, you skip E minus and E plus and look at the third nearest active line. Okay. And compute the intersection of P with that. Okay. If yes, if not, do nothing. Otherwise, if yes, then find the intersection of the ray with the third nearest active line. And intersection, if I call this R, then you output first R and then Q. Okay, in that order, R and Q. Earlier you see Q and R in that order, but in this case we have R and Q in that order. Okay. So that's the difference between the different types of events. So I am not giving you a detailed pseudocode for this. Instead, let me tell something about the data structures. Okay. Now in this case, the event QE is just the vertices of the input polygon. So what do you do with these vertices? You simply find min and delete min. So the sorting order is, Okay. So order is angle with respect to the horizontal position. Okay. Angle computed in the counterclockwise direction. Sorry, clockwise direction. Okay. So it seems that it's more or less obvious. This event queue, we do not insert anything other than the vertices. Okay. There is no intersection points like yesterday. So a simple priority queue will do. Min priority queue. So like a binary heap. Min heap. This will do. In fact, you have to make n delete mins. So each takes, so there are n vertices. So each will take log n time. So n log n. So even though you can do initially create that heap in big O of n time, you are anyway spending n log n time for this delete mins. So actually a sorted array is equally good. So initially you spend 10 log n time for sorting the array, and then one by one pick the next event, next event, next event, next event, next event, and so on. Okay. So that's fairly straightforward. What about S? S actually involves arbitrary insert delete and find min from time to time. Okay, so insert, delete, and sometimes find min. Okay. So since these are arbitrary insertions and deletions, we will use a height balanced binary search tree. Like a VL tree or red black tree. Okay. So is S, this ordering in the tree is with respect to distance from P along the ray, but these distances are not stored. Because exact distances do not matter. Only the relative position of the active lines, active edges with respect to these distances is important. But when inserting or deleting a new edge, okay, we will calculate the distances. Okay, during insert or delete, we just calculate the distance. Distances along only the insert or deletion paths, not in the entire tree. Okay. So there are n events which can be handled in log n time. Okay. And the size of S is never bigger than n. Therefore, it is easy to see that this overall running time is big O of n log n. Okay. Okay. So that's all about the algorithm. I am not giving you a very formal, I would say, pseudocode for this. We have seen how to handle each type of events. Let me now see whether I will proceed a little bit. Yes, I think I have spent something like 40 minutes. So I can continue a little bit with the next topic. So this is yet another topic which is important in its own right. So Voronoi diagrams. Okay. So I will first import a picture to show you what it is. Okay. 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 So, in the two-dimensional plane, you are given a set of points in general position. Okay. So, input a finite set of points in general position. So, what does general position mean in this context? Like no 3 collinear, no 4 on the same circle, and maybe a few other things. Okay. So, if you are given 3 non-collinear points, there is a unique circle, and we assume that no fourth point will appear on that circle. Okay. Okay. So, points in general position. Now, these points are often called sites. So, think of them as grocery stores. Okay. This is a grocery store, this is a grocery store, this is a grocery store, and so on. Now, if you live here, or if you are at any point, assume that all the grocery stores sells the same items, and the prices are also the same. Therefore, your only criterion for choosing a grocery store is proximity from your house. Okay. So, in particular, people of this region will prefer this because it is closest. Okay. Here in this region, they will choose this grocery store because this is closest. Okay. So likewise, you can think of the sites as the positions of mobile towers, cellular phone towers. Okay. So this is the region which is to be served by this tower, because this is the geographically closest to this tower. If you consider this tower, it will serve this region. Okay. So, in particular, or more specifically, I can define this thing. Given 2 points Pi and Pj, I define Hij is the set of all points in the Euclidean plane such that the distance between P and Pi less than equal to distance Pj. So, this is a half plane. Okay. And the Voronoi cell for the site Pi is the intersection of Hij j not equal to I. Okay. In particular, you see that each Hij is a convex region, and you are making intersection of some number of convex regions. So, each Voronoi cell must be a convex polygon like this, or a convex region with 2 semi-infinite edges like this. Okay, these are unbounded but convex. But these are bounded. Okay. But anyway, these are convex polygons. These are not exactly polygons because these are convex regions because of this semi-infinite lines. Okay. And if the set of finite set, if I call it S, then Voronoi diagram of S is a specification of this cells of its Pi. Okay, which edges appear. So, this edge, 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 this edge. It's a complete specification of this Voronoi cells by specifying this edges, finite and infinite. You get what is called the Voronoi diagram of the set of sites S. Okay. So to this end, we want to compute this. I will propose one n log n time algorithm if there are n sides. Okay. But this initially raises a question. This raises a question that there may be there may be as big as n choose 2 edges. Okay, let's once again look at this picture. So, this and this, they share this edge, and this is basically the perpendicular bisector between this and this. This and this share this edge. This is the perpendicular bisector of this line. Likewise, if I consider this and this is the perpendicular bisector. So, is it possible that all of the n choose 2 perpendicular bisectors play or contribute an edge, finite or semi-infinite, to the Voronoi diagram? Okay, edges in total. If this is possible, if every pair Pi Pj contributes a portion of their perpendicular bisector. But if there are about n square by 2 edges, I have to output all this, and therefore, how can I have an n log n time algorithm? So that's a very important thing. So, in reality, Voronoi S does not consist of big theta of n square edges. Why? Consists only of big theta n edges. Okay. And therefore, an n log n algorithm would be a reality. Okay. So, I will give a justification before stopping today. Why this is the case? So, once again, we import a diagram. This one. Okay. Okay, make it little smaller. It's too much. Yeah. Yeah. Okay. Okay, so first problem is we have semi-infinite edges, but we can choose some points a little bit away from this and assume that this will go up to infinity, but I will just cut it here. So we do something like this. Okay. So that I can talk about a bounded region with the understanding that this will proceed to infinity, but I just now have a finite figure. Okay. Now, these points, along with these points, consider them as the vertices of a graph. Okay. So, consider a graph G, where am I? Yeah. Consider a graph G equal to VE, whose vertices are these vertices, which are already part of the Voronoi diagram, plus this boundary. Okay, regions of this boundary, these points on the boundary. And edges are the edges of the Voronoi diagram, plus this. Okay. this construction says that this graph, which we can definitely draw on a piece of paper, this is a planar graph. Okay, because it can be drawn on a piece of paper, and you can see the drawing. And if I remove this drawing, then this gives us, let the points stay, this will give us Voronoi cell for this, Voronoi cell for this, Voronoi cell for this, Voronoi cell for this, and so on, plus one unbounded region outside this boundary. Okay. So these regions are called faces. Okay. So in particular, I have n plus 1 faces. So n faces corresponding to the Voronoi cells of each side of the n sides plus one unbounded region outside. Okay. Moreover, since no 4 or 5 or 6 points are lying on the same circle, you see that the degree of each vertex in the graph is 3. This is 3, this is 3, this is 3, this is 3, and so on. Here also it is 1 and this boundary, this boundary. Here also this and this. So, since the points are in general position, I can conclude that each vertex has degree 3. Therefore, by the degree sum formula, 3 times V is nothing but 2 times E. And this gives me F, number of faces, equal to n plus 1. And since this is a planar graph, I can use this formula V minus E plus F equal to 2. Okay. So then I have V equal to 2/3 E. So 2/3 E minus E plus n plus 1 is equal to 2 minus 1/3 E. So this gives me, move it to other side, minus 1/3 E. So E, 1/3 E will be n plus 1 minus 2, that is n minus 1. So E will be 3n minus 3 and V will be 2n minus 2. Now, definitely I have included these edges, this. If I forget these edges, I can say that the total number of edges that will appear in the Voronoi diagram will be less than equal to 3n by minus 3, and total number of vertices, which are no longer these vertices, this only, will be less than equal to 2n minus 2. Therefore, the size of the Voronoi diagram is linear in n. It's not too big, and therefore n log n algorithms are possible. So in the next lecture, we will see one such algorithm. Okay. So I think we can stop here. See you again in the next lecture. Bye.